let's go for the next presentation. We have Dandan here with us, and floor is yours.
Hello, everyone. My name is Dandan Yuan. I'm a PhD candidate at the University of Auckland. I'm very pleased to present our paper, Without Pattern Hiding, Conjunctive Searchable Symmetric Encryption with Forward and Backward Privacy. This is a joint work with Congzu, Shu Jiecui, and Giovanni Rossello. First, what is searchable symmetric encryption? In a typical model of searchable symmetric encryption, abbreviated as SSE, there exists a client and a server. The client has a lot of documents intending to outsource them to a server. The server is honest but curious. It follows the protocol, but tries to glean private information about database and queries. To enable efficient searches, the client needs to build the index from the documents. Here, this is an example. For the inverted index, the first line indicates the documents ID2, ID4 contains the keyword diabetes. SSE enables the client to encrypt the index and documents before sending them to a server. Then it can perform search queries. For instance, in a single keyword search on a keyword, the server can return the documents that contain the keyword to a client. Dynamic SSE enables the client to update the database. For instance, assuming the client has the latest version of the document ID6, which requires adding 2 keywords, the client can generate a token to update the index and the document set. Conjunctive DSSE supports conjunctive searches which return the documents containing multiple keywords. For instance, in this search on diabetes and SBP and headache, the server will return ID2, which contains all the 3 keywords. Conjunctive search can incur a leakage profile called the keyword pair result pattern, which refers to the intersection of documents containing any 2 keywords involved in a search query. For instance, in this example, if in this conjunctive search, if the server can learn ID4 contains both diabetes and headache, we can say keyword pair result pattern is revealed. And with keyword pair result pattern, the server can make file injection attacks to recover the plaintext information about the such keywords. So keyword pair result pattern should be hidden from the server. However, none of the conjunctive DSSE in the existing literature can achieve keyword pair result pattern hiding while achieving sublinear search efficiency. There are 2 previous work, Brandsteer and its XT can achieve keyword pair result hiding in static databases, but they all utilize static structures and cannot be extended to support updates. In addition to keyword pair result pattern, there exist 2 standard security properties for DSSE, forward and backward privacy. Forward privacy ensures an update reveals nothing about the updated keywords. And the non-forward private DSSE is vulnerable to file injection attack, so it's essential to achieve forward privacy. Backward privacy can ensure search queries do not reveal the deleted results. For instance, after deleting the keyword headache from the document ID4, then in a following search on involving the keyword headache, the server cannot learn ID4 was previously matched by the keyword headache. In this work, our design goal is to design conjunctive DSSE schemes that guarantee keyword pair result pattern hiding, forward and backward privacy while not compromising the search efficiency. To present our construction, I will first give our novel crypto primitive called attribute updatable hidden map encryption, abbreviated as AUHME. Then I will explain how AUHME be used to implement our DSS conjunction, named as DXSD. Then I will give analysis and possible optimizations. The setup algorithm of AUHME generates a master security key and a state. Then it can encrypt an attribute map to a ciphertext C. In our work, an attribute map can be considered as a set of key-value pairs where every key can be an arbitrary string and every value can be only 0 or 1. Given a predicted map P, AUHME can encrypt, can generate a decryption key from the P and run the query procedure. In the query procedure, if P is a subset of A, which means all pairs in P are all included into A, the query will output 1, otherwise it outputs 0. In this example, since the entry A2 does not match the attribute map, so the query can output 0. Here, the key security feature is if the query returns 0, it does not reveal which pairs in P are not included in A. Given an update, in this example, means updating the value of A2 to 0. AUHME can generate a token and run the apply UPD procedure, which will update the ciphertext C. Here, the security feature is an update will reveal nothing in update process. In our conjunctive DSS construction, the encrypted index consists T-map and X-map. T-map is an index supporting single keyword search queries, which can be instantiated with a single keyword DSSE. X-map is a AUHME ciphertext of a map, which maps every possible keyword document pair to a bit that indicates whether the pair exists in the database or not. We say a keyword document pair exists in the database if the document contains the keyword. For the index previous in the shown in the previous slides, the T-map and X-map should like this. Then in a conjunctive search, diabetes and SBP and headache, the client first perform a single keyword search on diabetes. The reason why the client first search on diabetes is that diabetes is the least frequently occurring keyword. Then the client can get the search result on diabetes, which is ID2, ID4. Then for ID2, it will generate a AUHME key to query why the ID2 contains both SBP and headache. Also for ID4, it will also generate a decryption key. And the server will run AUHME queries over the decryption keys and the X-map. In this example, it will discover the first decryption key can make the query returns 1, and the second will make the query returns 0. Then the server will return, will notify the client the first key can work. After that, the client can know ID2 matches this query. In this process, we can say that the server could learn ID4 contains the keyword diabetes through the single keyword process, but the security of AUHME can ensure the server cannot learn if ID4 contains the keyword headache. This is the key to achieve keyword pair result dependent hiding, since the server cannot learn if ID4 contains both diabetes and headache. Given an update, the client generates a token to update T-map and invokes the Gen UPD algorithm of AUHME to get a token. The token will update the X-map. For security of HDXST, if a T-map is instantiated with a forward and backward private DSSE, HDXT can achieve forward privacy, backward privacy, and keyword pair without independent hiding. For the performance, the search performance is very good, which only linear with the number of documents containing the least frequently occurring keyword multiplied by the number of keywords involved in a search. We have done some experiments which can show our search performance is very good in search time and communication overheads. Our trade-off lies in the update and storage complexity. In the worst case, update complexity and the server storage overhead. The overhead can be linear with the total number of documents multiplied by the total number of keywords. And in our paper, we have done extensive comparison and experiments to show this trade-off is acceptable. Also, there are methods that can optimize the update performance and storage overhead. And for improving update performance, if you are interested in, you can see our appendix. And to reduce storage overhead, we can only store the information about frequently occurring keywords in XMAP. Then in a conjunctive search, we can first perform single keyword searches on infrequently occurring keywords with T-map, and then filter out the documents that do not match frequently occurring keywords with XMAP. Thank you for your attention. Do you have any questions?
Thanks, Dandan. So one question, the attribute updatable hidden map encryption that you build has some similar functionality to private set intersection cardinality. Have you seen whether the new techniques that are developed there can be applied here to achieve more efficiency, or any specific relation between these two primitives?
Sorry, I didn't understand your question very clearly.
So the new primitive that you are building, the attribute updatable hidden map encryption,
Yeah.
the functionality has some similarity with private set intersection cardinal.
Private set intersection. That's not the same case. Since for EU HME, it's supposed subset query, which means, for instance, the client already has a subset, and it will query the server whether this subset belongs to the big set. But for private set intersection, it means it just computes the cardinality, not the subset query, and also our EU HME cannot support check the cardinality. We only can return 1 and 0.
Thanks.